Hello there, good afternoon, good evening, wherever you are. Welcome to Codebase Alpha. This is a continuation of the last stream that we did, where I was looking at two things. First, I was looking at the video RAM of a Spectrum 48K, and also trying to code some input-output instructions for our Z80 emulation. So we'll just continue straight on with that. What I'm going to do is to just drop back into the video RAM discussion that we kind of left off last time, and also talk about input-output instructions and continue try and code those, because that's all we've really got left to code to finish off the emulation. There's a few little kind of more esoteric bits and pieces to do, but that's the kind of the plan. I'm not sure how long I'm going to go on for this evening. Pretty tired at the moment. There's been quite a lot of events in real life which are kind of taking a toll. So let's see how long we can go. So let's just pop over onto our coding stream, a coding screen, and this is some of the kind of notes that we went through last time. We're talking about the layout of the Spectrum 48K video RAM, which is the kind of machine we're using. It's a very simple kind of a microprocessor system, games machine basically, which you could program in BASIC and also in using assembly language. But it's quite simple in its design, so it's an ideal thing to use as a little bit of a kind of a realization as to do something with the Z80 emulation that we're building. The concept that we're coming across is trying to produce a NuGet package, which we can just put up on NuGet or on GitHub, and anyone can download that, and they'll have an accurate Z80 emulation they can use. But we need to kind of demonstrate it actually doing something. We've had a few simple assembly language programs that we've built, so I thought let's actually try to get it to do some kind of emulation of a real system. Now the intention is not to go through and do a full emulation of the Spectrum 48K, because it might be quite complicated. We may do it, but at the moment what I want to do is have a program in BASIC on the emulation. Just to kind of recap what we did last time, the video RAM for the Spectrum 48K lies in the range of 400 hex to 57FF hex, and what that is, it's a block of the actual the RAM that's available to the Spectrum. Remember, we've got 48K of usable RAM. The first 16K is in the ROM chip, which contains basically what we call the operating system, and then from 4000 to 57FF is an area of memory where we poke values into there, and those get translated into characters that appear on the screen. And if we look at the actual structure of one of these addresses, you can see it's split up into these 5 different kind of segments. The first 3, the highest significant bits, the most significant bits here, these 3 here, basically are fixed, because that simply defines this range. The next 2 bits define which third of the screen the video RAM is kind of looking at. So there's kind of, if you imagine we've got it's a 32 by 24 character screen that we've got. So that is split into 3 8-line segments. So we've got a top, a middle, and a bottom, and that's what these 2 bits here define. So this 10, that's a value of 2 in decimal, and that means we're talking here about the bottom third of the screen. The next 3 bits are the pixel line. So each character is defined by an 8 by 8 grid. Of course, what you'll see here is you've got 8 lines. Each line of that is a byte, with 8 bits, of course, in a byte, and we've got 8 of those to make up an 8 by 8 character. So this, with a value ranging from 0 to 7, basically 0 is the first line of the character sprite, you might say. 1 is the second, etc., down to the bottom one, which is 7. Then you have which line you're on within the third, so 0 to 7, that's 8 lines within the third. And finally, we've got the character. Which character are we looking at? So that is 0 to 31 available here. There's some obviously not used, and that is the 32 lines. Fjord Stable, I wonder how they came up with this scheme. I don't know. It's a bit weird, isn't it? So yes, I would have kind of moved these around. I'd have had third of the screen, the line, and then the pixel line. And then maybe the characters on the end is quite okay. But yeah, it's very strange how they came up with it. Okay, so that really kind of defines what we're looking at. Last time, what we did, we ran our emulator, and we loaded up a Spectrum 48K ROM, and we ran it for a few minutes, and then we dumped out the video RAM area. And what we did then was to just go and have a look at what was in there, and I chose the very bottom line of characters because there was data there, and we worked out that basically for character 0, we looked at each of the 8 values of the pixel lines, so line 0, 1, 2, 3, 4, 5, 6, and 7, and we found out what bytes were stored at those locations, and they were respectively, there was 3C, 42, 99, A1, A1, 99, 42, and 3C. And this looked quite promising because there's a kind of a pattern there. And what I did is then I kind of decoded that, and we found it was this character. So it was a copyright symbol, which is quite pleasing because we've never actually seen any output from our application before. So that is what we got as the very first character on the bottom line of our screen. Well, in the video RAM, that's what was there. So what I decided to do then was think about kind of actually visualizing something. And actually, Fjord Stable put in a pull request to the project to do something with the debugger to try and visualize some output. And that's using a writable bitmap in the WPF application. And I've accepted that and pulled that in and had a bit of a play with it, but not done an awful lot. But what I have done, and I'll show you the code once we actually run it. This is the code that we've got. Is I've pulled in something called the Pixel Game Engine, which is it's a C++ header file which was created by a friend of the stream, JavidX9, otherwise known as the One Lone Coder. And I'll just pop actually a shout out to him, JavidX9. He does his Twitch streams as well, but does a lot more on YouTube. And he has this fantastic kind of very simple to use basic game engine. So there's a game loop in there, and it does graphics, pixel-based graphics, and it does audio. And it can actually do 3D graphics as well. What I did, I found that a guy called DevChrome, I know nothing about it in his handle. DevChrome actually created a C# port of it, and so I forked that repo and decided to give it a go. And so over in this project, I created a new project within our solution called SMB Spectrum 48, and I built the Pixel Engine DLL and dropped it into a library folder here. So that's actually up on GitHub. So if you wanted to kind of play with this and you downloaded this project, you would get a fully compiled version of the Pixel Engine. But I say I do have a fork of the project as well, so I can change it. We've also got the Spectrum 48K ROM, which is uploaded onto GitHub as well. So when you pull down this project, you get that as well. And what I'll do is I'll run the project. And as per such, thank you very much for the subscription. Let's have some hyperspatial hype to celebrate. So thank you so much for that. Yeah, I haven't seen you for a while, as per such. So it's really good. You'll be catching the recordings. Well, the reason why you haven't caught me live is I had quite a long break. There's been quite a lot going on in real life, which really came to a head in the early hours of this morning. So hopefully we kind of, once we get various kind of practicalities out of the way, things will kind of return to a bit more normal, and I'll get back to broadcasting, twice a week at least. But it's been a bit up and down, and it's sometimes real life is more important than streaming. So, but I do want to get back into the regularities. So let's run this project, and remember that we're looking for, on the bottom line, we want to see a copyright symbol. Let's run the project, and then I'll go through the code, and we can have a look at what it does. So let's run it up. I'll click start. Okay, and here we go. Okay, there we've got, so see, here's our copyright symbol. We've got a space, and we've got 1982 Sinclair Research Limited. So we actually have some screen output, and you can see up here we've got, I don't know if you can actually see, we've got a frame rate here of around about 50 frames per second, which is the kind of frame rate we want to get out of this this processor. Now it's all kind of been it's been kind of architected really, so it tries to give us as close to 50 frames per second as we can. That's kind of the refresh rate of the video in the UK, 50 Hertz. I'm not sure, obviously the processor's doing nothing at the moment, so the emulator is actually just in a loop at the moment, looking for keyboard input, and we haven't done any keyboard routines to get input into the process, so hopefully in the next coming weeks we'll be able to do that. So that's it. And it was full colour. Did you notice that it was? It looks blurred. It's not. It's the reason why it might look a bit blurred is it's this funny grey colour with black writing. Now, there's that, and there's also quite a wide border. There's a 48 pixel border around the actual screen, so the screen is kind of in the middle here. And on the real machine, there was actually quite a wide border, so it's 48 pixels. Side to side, and 48 pixels at the top, and 56 pixels of border at the bottom, and it's actually this strange grey colour, which is not the correct grey colour yet. We'll play around with the definitions of the colours to get actual accurate spectrum colours from it, but at the moment it's not. So if it's a bit blurry, it's also quite small. Could you overscan on MX Spectrum? I'm not sure if you're stable. At the moment, I'm not. I haven't delved an awful lot into the actual architecture of how to fully emulate the spectrum. At the moment, what we're doing is kind of it's pretty coarse, and it's not the. If I was having to do kind of the games playing on this emulation, we'd have to get things like timing very accurate and synchronization very worked out, and we may get into that, but I'm still very much a beginner at this kind of emulation game, so I don't want to get into that prematurely. What I want to do is see if we can get some input into this and write a basic program in it, and that's kind of, I'll figure that's a pretty big win. Okay, let's stop this and let's have a look at the code. Before we look at the code, what I will do is actually explain the colours, the way colours work in the spectrum. So, as I said before, the video RAM, the VRAM, runs from 4000 to 57FF, and then from 5800 we have 768 bytes, and this is called the attributes. Each byte is going to be representing a character on the screen. Remember, a character is an 8x8 kind of block of pixels, and the byte is going to give us the colours that we need to display. So if we look at an attribute byte, write down the bits. We got bit 7, 6, 5, 4, 1, and 0. Copper Beardy, welcome. Good to see you. Sorry, did you post a link? I'm sorry if you did post a link. I'll sort you out with a VIP badge after the stream, and then you'll be able to post links. But if you want to post a link, just kind of encode it so that Nightbot doesn't recognise it as being a link. Fortunately, I've got Nightbot wound up right up to the highest possible settings to try and keep the stream safe. So I do apologise that you got kind of a block there. Okay. So what do these various bits signify? So with bit 7 is the flashing bit. So if that is set, then the colours basically will invert every 16 frames. So this is every 16 frames it's going to flash. Now I haven't worked out how to do that. So we don't have flashing. We're going to invert colours. That's that one. The next one is the brightness flag. If this is set to 0, then we're going to be using dull colours, and if it's set to 1, we're going to be using bright colours. These set of 3 bits here. Remember here we've got 0 to 7 is the possible values of those 3 bits. This is what we call the paper colour. So that's basically the background colour. And these ones here, once again we've got 0 to 7. This is the pen colour, i.e. the foreground colour. Okay, basically we've got if it's 0, 0, 0, then this is going to be black, and it's going to grade up all the way to 1, 1, 1, which is white. If we think about the brightness bit here, there's no such thing as a bright or dark black, really. It certainly isn't in the spectrum. So bright black and non-bright black are the same colour, but the other colours are basically they're kind of blue, red, magenta, cyan, whatever. And then white is either a grey, or if the brightness flag is set, it's a kind of a white, bright white. And I think, for example, the reason why it may have been a bit was it Nightbot was warning me for the shout out? That's very strange. It shouldn't do because I'm the broadcaster. It shouldn't. Okay, well that's really weird. Who knows about Nightbot? As I was saying, the reason why it may have looked a bit blurry on the stream, and I will look at it back on the stream afterwards, is it's not quite the right grey colour, and it is grey background and black pen, which is a bit weird. So that's the kind of how the attributes work. So let's go and have a look at the code. AI is taking over. Okay, so let's have a quick look. So currently this class is still called SimpleBus. So what I've done is added some code to our implementation of IBIS. IBIS remains the same. I've not added any new functionality to that, but we've got some extra attributes and extra methods that have been added. The first thing is a flag which says when the screen is ready. So when we've painted a full screen, all 192 pixel lines or scan lines of the screen have been painted, then we set screen to ready, and then that is read by our program. We've also got the border color. This is the color of that band around the outside of the screen. Remember, it was 48 pixels either side, 48 pixels at the top, and 56 pixels at the bottom. And as you can see, I preset this to a black color. Yet when we ran the emulation, then it was grey, and that's because that color came through from the ROM. One of the very first things that it does is set the background, the border color, and I can show you that. If we go over to the here, and I think if I find the ROM index for the spectrum here, and we go to the start. Obviously, we start running the ROM at 0 hex, you can see here where you can jump to start. Okay, and this line here, 11CE, it says use the out opcode to send out to this port FE, the value in the accumulator, and that value was 7. And you can see it says here in the comments, make the border white in color, and it's a dull white. So I'll interpret that currently as grey. I'm going to just check with some Spectrum owners to see if it is white or if it is grey, that colour. When you do the border, there is no distinction between bright and dull colours. So there's no way of making it bright white as such. It may be that it's interpreted as bright or dull, but you can't control the colours to that effect. Remember, with this combination of colours that we defined up here, we've got potentially 16 different colours, but 2 of them are exactly the same, the black. So there's actually 15 different colours that our Spectrum can output. Okay, so that's so we can see that command there. It's quite early on, so it's only like I think there was 4 or 5 opcodes before this. So it's very early on. It changes the border color, and we actually saw that happen. We've got some standard stuff here, and then we've got some new private variables here. So we've got a counter for which line we've rendered on the screen, which pixel line we currently operated on, which screen line, which physical kind of character line we're working on. We have a screen buffer, which is a Sprite, and Sprite is a class that's defined in the Pixel game engine. What we're going to do is we're going to build that Sprite up behind the scenes, and then we're going to display the Sprite, which is the entire screen, all in one go. So we're not going to have we're not going to see the scan lines. We're going to build the scan lines in the background and then flash up the new screen. And what we're aiming to do is that about 50 times a second if we can. At the moment, it's very kind of difficult to know exactly how that's going to operate when we actually have this emulated CPU doing some actual work. We'll see. Hopefully in the end anyway. Then we define where the video RAM, the screen, starts at 4000X, and the attribute block, as I say, starts at 5800 and is 768 bytes long. So just some definitions there. And then we have the pen and paper and brightness values. And the reason why there are 3 different values is because I've decided, for better or worse, to actually build the screen up in thirds. So we're going to paint the first row, the first pixel row of each third simultaneously. So basically, 64 calls of our screen render will build an entire screen. So whether that's the correct decision, not quite sure, but that's what I decided to do. Then we got our standard kind of definitions of our IBIS methods, and then we get some new methods. So we've got a get screen, returns a sprite, and it basically passes back the screen buffer sprite. Then we've got run renderer, which currently just steps the render engine once. The render engine, it kind of glorifies it a bit. It's not there's nothing very clever about it. And this code is pretty much based upon stuff that FuelSnable submitted in his pull request. So I kind of pinched some of that code and played around with it. So as I say, what we've done here, we've decided. So every time we pass into here, the idea is to kind of paint onto the pixel, onto the sprite, one row of pixels. So that's 256 pixels across the screen, and we're going to do that for the top. Well, in the initial call, the top of the first third of memory, top of the second third of memory of screen rather, and the top of the third. So that the top, the middle, and the bottom. and we're going to call this, and after we've called this 64 times, we'll have reached the total of 192 rows we needed to paint, and then we say, okay, the screen is ready, and then our emulation will actually pop up the sprite on the screen. As you know, there are 32 characters on each line, so what we need to do is to scan through on each pixel line. We need to find out what characters are there. So we're going to go from 0 to 31, and we're going to grab the bytes at those memory locations. We'll ignore this slightly for just a few minutes. Then once we've got each of the characters, each of the bytes, then we need to scan through the bits that make up that byte. And so we read each of the bits, and we say, okay, is it on or off? Is it a 1 or a 0? Which is what this code does. Okay, and we work out what position on the sprite we are, and then what we're going to do is we're going to write onto the screen buffer at position X, which is defined here, and then the line rendered plus 0, plus 64, or plus 128. So we've got the top third, the middle third, and the bottom third. And what we say is, if it's not 0, then we're going to paint the foreground color, the pen color. And if it is 0, we're going to paint the background color. We do that for each third, and then we scan across each of those 32 characters. Increment the line rendered, increment the pixel line. If the pixel line is greater than 7, then we 0 it and increment the screen line. If the screen line is greater than 7, then we 0 it. If the number of lines rendered exceeds 63, then we set the line rendered to 0, and we set the flag screen ready to true. And there's something which then kind of reads that. In terms of this piece of code here, what this is doing, it's saying that because each byte of attribute refers to a complete 8x8 character, it would be very wasteful to read the attribute byte more times than as required. So only if we're rendering a line which is line 0, line 8, line 16, line 24, etc., up to line 64, then that's the only time we need to actually interrogate the attribute byte and find out what the colors are. And simply to actually read the attribute bytes for each character, we simply get the memory offset, which is calculated here, and then basically just do some bit shifting to get the pen, paper, and the brightness values as integers. And then in this method here, get colored pixel, we simply got a couple of switches, which is this is bright. Then we if it's not bright, that is, we choose the dark values, and you can see here is grey. And this value isn't quite the right RBG value, so I shall be redefining some of these values. And if it is bright, then we use the kind of ordinary colours. And you can see black, blue, red, magenta, green, cyan, yellow, and white. We return a default of white. So that's how that bit works. So that's quite simple, and I will be kind of pulling some of these methods off into another class at some point, just to tidy this up and get back to having the bus that it just defines the values, the properties, and the methods that IBIS needs. Let's have a look at the program. Okay, so this starts off quite similar to the sample project which I was working with last week. So fuel stable, consider load line rendered into a local variable. There's a risk that it's constantly dereferenced, taking a few cycles. That's a good point. So I've not really done an awful lot in the way of optimization yet. But you're right. So we should put it into a local variable. As you say, my CPU is very, very powerful. So I'm not for my personal preferences. I'm not worried about it being a drag on the system, but I do want it to be kind of generic code and be run by people who don't have such massive kind of massively powerful CPUs that I've got in my machine here. Okay, so we're defining where the ROM file is going to be. We've got an origin here which is at 4747, so this is basically where the screen is going to appear in the middle of the border. We've got our RAM, 65k of RAM. We've got our 64k RAM. We've got our a counter here, which is I'll show you. This is render tick. So we need to try and achieve something approximating 50 frames per second. So this is how I'm doing it currently. I'm well open to any suggestions or pull requests and to improve a lot of this code. Still very much kind of changing and fiddling with it to see what we can do to make it better. Actually, I'm missing some music. Let's get some music going. There we go, that's better. Okay, a bit of relaxed daily is what we need. Okay, so when you create a program using the Pixel game engine, you have a main method. We create an instance of our program. We call the constructor method with the dimensions of the screen. So this is we have 32 characters wide. Each character 32 character is 8 bits wide, so 8 pixels wide, and we have either side 48 pixels of border, so that's where the 96 comes from. So that's the width of our window, and then the height of the window, obviously it's 24 characters high, 8 pixel rows, so 24 times 8, which is 192, and then we had 104 pixels, 48k pixel border at the top, 56 pixel border at the bottom. And then this 2 and 2 simply means that each pixel will actually map to a 2x2 actual screen pixel. So we can increase this, so we can say this is going to be a 3x3. If we run this now, we will get a kind of almost like a zoomed in screen. So it's bigger, as you can see, and it takes a little longer to come up. So now it's a bit bigger. Now, is that still blurred? Pure stable, you're saying it was blurred, so it's a bit bigger now. This looks a bit blockier, that's all. So that's what those do. So the two values at the end are basically kind of a zoom value. So it's each pixel we paint is going to map to a 3x3 screen pixel. And then we call the start method, and that basically starts the game loop. Looks better. Okay, we'll leave it at 3x3 for the purpose of the stream. You raise the stream resolution. Oh, well, never mind. Okay, so then the next method we have to override for the Pixel game engine is Oncreate, and this is where we do our setup. So we define the size of our RAM. This isn't particularly genuine. We clear the RAM, so we set it to 0. On a hard reset, the Spectrum actually had random values in its RAM, so we should really randomize it, but I didn't see the point. We read our ROM file in here. So this is going to load the ROM here into the first 16k of our memory array. Then we instantiate a new instance of the Z80 emulation, and there's a new value that we can pass into it now, which is the clock speed. And this is me trying to get the timing to be as it should. No, I haven't done any measurements at all. I don't know if the timing is correct. But what the Spectrum 48K was a whopping 3.5 megahertz processor. Yeah, in these days, what we have for 3.5 gigahertz processors, don't we, or whatever. So yeah, 3.5 megahertz. So that's in terms of our emulation, we're looking at each of the T-states, each clock cycle being, I don't know, around about I don't know. I'll do the calculation, but if it was 4 megahertz, it'd be about a quarter. It'd be about 250 nanoseconds per cycle. Everything improved with about 1,000 times. Yes, everything did. Except memory latency. Yes. Yeah. But it's interesting that the memory in those days was very slow to access, though. So I'm sure that RAM these days it is a lot faster than was used in these devices. So whether this is actually causing my Z80 emulation to run anything like the correct speed, I've yet to determine. But I will add some telemetry to it at some point to figure out how fast it's running. We connect our CPU up to our bus, and then work out how many ticks approximate to 50 frames per second. Now this is obviously going to vary. The number I wanted in here was 3,200, which is 50 times 64. Remember that we want it to run at 50 times a second, and each run of the renderer needs to write 64 lines in the top third, middle third and bottom third. Your old Atari, for example, says had 120 nanosecond memory, which is fine on a machine that uses 8 megahertz. Absolutely. So this is, I've got a comment here saying tune this value, looking for about 50 frames per second. So I'm playing around with this value. I've settled currently on 4,000. The next method and the only other method we actually have to override is the OnUpdate. And basically what this is, we've got a game loop that's running, and this OnUpdate is going to be called as we kind of cycle through the game loop in the background. We clear the screen with the border color. If the window has focus, we can press the escape key to reset our CPU, and I'll show you that. And then, while the screen isn't ready, then we start a stopwatch. We run the renderer once, so that's one render step. Remember, run render currently only does one step, so one line in the top, middle, and bottom thirds. And then, while we haven't reached our render ticks, and the screen still isn't ready, then step the CPU. So it'll stay in this loop. It'll exit here when if the screen is ready, or if we've run out of render ticks. So this is where we've got I don't know however many ticks this is. So this, I think, work out how many ticks that is. Let's go calculator. So on my hardware, I looked at the stopwatch frequency, and that was 10 million. And then we want to divide that by 4,000 in this case. So that's 250 ticks. So what we're saying is every 250 ticks on the stopwatch, then we're going to call the renderer basically. If it happens that we run out of ticks and the screen still isn't ready, then we'll start again. We'll run through again. We'll run the renderer once more, and then go into this calculation. So if we kind of exit, if the screen is ready early, we'll exit out of here, and if we run out of render ticks and we still haven't quite finished writing the screen, we'll go into it again, but come out quite quickly. If we drop out of the while loop, then we set our screen ready to false. We update our window title. It's got an approximation of the frames per second in there, and we draw our sprite. So remember, we call get screen, which is getting our buffered sprite and displaying it on the screen. So that's what happens. So if we start this up with very little code, we get something which in about 4 seconds actually displays the Sinclair Research copyright. So I understand that the real Spectrum would boot in about 2 seconds. So we're not doing too bad in 4 seconds. But I'm not rendering the screen in the way, obviously, that the real Spectrum would have rendered it. It would have rendered it one line at a time. You can imagine an electron gun swooping across the CRT screen, flying back, swooping across light. So it would build it up sequentially, one line at a time, going down. I'm building it up in thirds, just because I felt like doing it that way. There's no particular reason. If I press the escape key now, you can see here we're getting approximately 50 frames per second out of the emulation. If I press the escape key now, we're going to just reset the CPU, and we go through the boot up again. And those red lines you see that briefly scan over there, that's basically the memory test. So those lines are simply the memory test kind of running through the video RAM, and it goes on obviously through the whole 64K of memory and test it all. So that's that. As I say, what we got here, is less than 100 lines of code, and we've got the basis of displaying a screen, and we've also got the facility here built in that where if that window's got focus, we can actually take input, and actually we can also produce audio. So the thinking is that I'm going to utilize this game engine to detect key presses on my keyboard, translate those into the keyboard matrix signals that the Spectrum would expect to receive, and see what happens. I'm still not quite sure exactly what the mechanism is for reading the keys and then displaying the keystroke upon the screen, but I think it's going to involve interrupts. But we'll come to that. Also, we're going to need to at some point try and emulate single channel sound. So I think a couple of octaves worth of simple notes that the Spectrum could output. Nowhere near as comprehensive a sound system as something like the Commodore 64, for example, which had quite a good sound chip, the SID chip, in that could produce quite a lot of music. And in fact, you can actually still buy Commodore 64 cartridges which have a MIDI plug on them, and you can plug that into a MIDI keyboard and use it as a synthesizer. It's not particularly user friendly, but it does sound really good. So who knows? And on speaking about Commodore 64s, last Wednesday I took delivery of the C64 Maxi. It's upstairs in the bedroom at the moment, and I haven't really done anything with it other than to update the firmware. I hadn't had the opportunity with things that are going on in real life at the moment to actually sit down and have a play with it. So I'm looking forward to doing that at some point. But that actually arrived, and I'm really pleased. Okay, so that's what we did there. Cosmic Bakery. What's that for your name? Do explain. Comic Bakery. Okay. So what changes are made to the Z80 emulation? I haven't done an awful lot. So let's just have a quick look at what I have done. Down here we have a new property, which is Z80 clock speed. Basically, we set this in hertz, and we use this calculation to figure out how many microseconds each of our TStates should occupy. What's this? Oh, Commodore 64 tunes from the day. Yes, I think they're really good. Well, you know, relatively speaking, for a 1980s computer system, they're pretty impressive. So if you'll remember, a T-state is a single clock cycle, and our instructions are the length of time an instruction takes to run is measured in T-states. So for example here, doing nothing, the no operation, the NOP operation, actually consumes 4 T-states. So it's going to kind of go through 4 cycles of the CPU. And the reason why it's kind of 4 to do nothing is it's actually got to read the instruction out of memory, and that takes 4 clock cycles to do. So if we're running, for example, at 4 megahertz, which is kind of the default I've defined in here, that's actually going to take about 1 microsecond to do. So if yours says, I think it's interesting that when I was a hacker, I was envious of Amiga 8-bit samples, but when listening to an old songs, they had to sound quite bad, even though the song is nice. Yes, well, it is pretty. It is. It isn't great, but chip music, yeah, why not? I've heard some really good stuff. There's a guy on YouTube called Adrian Black, who basically he buys old computer systems from C16, C64s, all the way up to IBM PCs and Macs, old Macs, and he repairs them and gets them running again. His video series is called Adrian's Digital Basement, and he actually plays chip music on his videos because he has kind of time-lapse sequences when he's doing lots of soldering and stuff, and he plays kind of chip music. It's up-to-date stuff, and it's really quite good. As I was saying, this is the number of T-states, number of clock cycles that doing nothing takes. So 4 clock cycles, which is on a 4 megahertz machine would be 1 microsecond to do nothing. Here we can see incrementing the register pair BC will take 6 T-states, etc., etc. And some of these operations actually take quite a lot. I'll come down to some of these. You can see here, and the reason why they're broken up is because each there's more than one kind of thing going on. There's a memory access or a write or a process that's going on, and each takes a different number of T-states. But the total of this, so 10, 16, 20 T-states, 20 clock cycles at 4 megahertz to do this instruction. So this is how I'm trying to get it so it runs at the right speed. I'm not quite sure it does yet. So, Jock in the Frock, welcome. Dumb question, and you here. You're building a Spectrum emulator using Javic's Pixel Game Engine? No, that's not really the object of the stream. But what we're doing is building a Z80 emulation in C#, which is what this is on the screen at the moment. And what I wanted to do is actually show the Z80 emulation doing something which was a bit more engaging than just running some assembly language, which is what we got it doing first. So we have a debugger written in Windows Presentation Foundation, and we can load up a program, and we can step through the program and see it actually updating all its registers and producing a result. But what we did is wanted to just see it do something which I hadn't programmed. Loaded up a 48K Spectrum ROM, dumped out the video RAM, found it was writing characters to the video RAM. So that's when I'm a big fan of Javid X9, a well-known coder. I knew his Pixel Game Engine quite well, so I grabbed a C# port of it from DevChrome, and then it was very simple to hook up. One thing I didn't want to do is spend ages trying to get some kind of video display when that's not the point. What we're trying to do is get a NuGet package for a Z80 emulation, which is very accurate, or as accurate as we can make it, to which anyone can then download it using their projects. But this is just kind of a fun thing to do, and we'll take it as far as we can. I mean, we might even do different machines. I did want to do an Amstrad CPC, for example. It's a lot more complicated architecturally, and the problem is finding information on the internet takes time to actually build up the knowledge to do the emulations. Okay, so that's how we work out the how long a T-state should be in our emulation, depending on what speed our processor will be running at. We default our processor speed to 4 meg. I've overridden it in the Spectrum 48 program. And then we have down here we have a wait function. So this here we're waiting 17 TStates, and wait simply uses a stopwatch here and works out how many ticks it's got to wait in order to kind of be asleep or spinning for that length of time. And of course, the problem we've got here is that my stopwatch frequency is 10 million on my hardware, so we can't go above 10 megahertz in our kind of emulation. Luckily, I think Z80s were around about 3 to 4 megahertz, maybe even up to 8. I'm not quite sure of where various people might have pushed the clock speed up. Okay, so that's basically all that's changed on the emulation. We're now trying to get it to run at a realistic speed, and so I don't know if we've achieved that yet. Okay, so let's do a bit of coding, shall we? The last time we were working on input-output, and we only actually got one opcode written, and it didn't work by the end of the stream. The tests failed, and as is always the way, I ended the stream saying, "Oh well, I'll have to think about this." And within 5 minutes, I spotted what I'd done wrong. It always happens. The kind of pressure of the stream is quite telling. What I did wrong is I was decrementing the register pair BC instead of just the register B. So that was what's causing all the tests to have the wrong values for BC and the wrong values for the flags and the wrong values for the mem pointer. So I fixed all that, and that's this code here. And if we run our unit tests now, let's bring them up. And remember, the emulator should is the one we're interested in. Let's first run it not in debug mode. So we should run through. We got 279 tests apparently, but in fact, this last test here, well, one of these tests is actually running a lot more than 279 tests. So let's run it again in debug mode. Just run this one, and we should stop here. Okay, so we've got no tests failing. You can see we've got 1,235 tests passing here, and these tests are written by somebody other than me. So this is there's a project called Fuse, the free Unix Spectrum emulator, and they wrote these tests, and there are about 1,300 of them. So we got 1,235 passing, non-failing, and 121 tests which we've not written the code that those tests exercise. So that's what the kind of plan is for this stream. We'll get a few more commands written. Okay, so let's have a look. So currently in the input-output group, we've got in A, which is basically bring a value from a peripheral into the accumulator register, output the value in the accumulator to a port, a peripheral port, and then in, which is going to bring in a value from a specified peripheral port into a nominated register, out, and then we've got INI, which is in an increment. So bring a value in and increment. What we're doing here is we're looking at the port which is defined by the value in register C, and we are dragging that from the peripheral and putting it into the memory location pointed to by register pair HL. Then we decrement the B register and increment HL register pair. So basically what that's done is simply read a value and put it into a memory location. So where the tests kind of make this a difficult task is we need to figure out what the flags, the various status flags in the CPU get set to. And there's also a undefined register called Q, which basically has a copy of the flags, and also a rather mysterious value called memPointer. And these values, they're not documented in the original documentation for the processor. They are things that people have worked out afterwards. Luckily, obviously these Z80s are around in the 80s, and some people have spent a lot of time working out exactly how they work, what undocumented features they have, what undocumented commands they have, and there's quite a lot, and also what bugs they've got. And there are bugs, so we're trying to emulate the bugs in the original hardware, as well as how it's supposed to work. So in this case, if we look at the flags that get set, I've said we're actually going to set all flags and undocumented features. Yes, there's lots of them. Luckily, they are now documented. So if we go over to here, this is the Z80 user manual. This is the INI command, and it says the S flag, the sign flag, we don't know. According to the user manual, they didn't know how that was set. They didn't know how the H flag was set, the parity or overflow flag was set. The N flag, it says it is set, but that's not speaking true, and it says the carry flag is not affected, and that's not true either. Okay, so this is what the documentation says, and then if we go to the undocumented stuff, so we've got a PDF here called the undocumented Z80 documented. In here, if we go and look at, excuse me for scrolling down quickly, I'll find the location, then do some. Then I'll zoom in a bit so you can see it. Okay, it says I/O block instructions. These are the most bizarre instructions as far as flags are concerned. So it says all the instructions, the sign flag, the 0 flag, and 2 undocumented flags are affected as per the decrement operator. Well, that's not what the user manual said. The user manual said that the S flag, he didn't know how that was changed. It says in the user documentation, it says the N flag is always set. Unfortunately, that's not true either, because over here it says the N flag is a copy of bit 7 of the value read from or written to an I/O port. Jock in the Front, did I build a subroutine for each opcode and then build a main program or loop to run your code base? Yes, basically. So what I've got is a massive kind of dictionary or set of dictionaries which each point to a function, and I wrote the code for each function. There's a step to go through at some point to can rationalize those subroutines. So they're often have got a bit of repetition in them. So I need to go and extract a common code into common subroutines, and so it breaks it down nicely into different methods. But yes, basically I've got lots and lots of functions which are being called. I'll show you how that works in a second. Down the bottom here we see that for INI, which is the command we were looking at, there's quite a complicated way of setting half carry flag and the carry flag. And remember, it said that the carry flag was unaffected, and that's not true. It's affected by this logic here. And the parity flag, it says it didn't know, and that's actually set by this rather more complicated logic. which involves some ANDs and some exclusive ORs. The other thing is there's something called mempointer. This is a document which you can find on the internet, and if you come down here we'll find INI. It says that this mempointer value is the value of BC, register pair BC, before it's decremented, plus 1 for some strange reason. So there's a lot of kind of figuring out to do, and that's why having these independently written tests is fantastic, because when the tests pass I know I've got the flags set correctly. And that's what kind of flummoxed me last week, in that because I was decrementing the whole of the register pair BC rather than just register B, nothing would work. But after the stream finished I noticed, and then we were away. Okay, so we've got INI. So the next in the list is INI-R. This is simply INR repeated. So we're going to do exactly the same thing. We're going to look at register C, and we're going to use that as the I/O port. And we're going to read a byte from the I/O port, and we're going to stick that byte into the memory location pointed to by the value of register pair HL. That's what the brackets mean. It means they're pointed to. Then we're going to decrement the B register, not BC. We're going to increment HL. So it's exactly the same as the command we've just done. However, what we're going to do is if the decrementing of the B register goes to 0, we stop. But if it doesn't, we're going to decrement the program counter by 2. So the program counter points to what the next instruction is going to be run. If we decrement it by 2, remember we're going to be pointed after this byte here. Decrement it by 2, we're going to be pointing back at this byte. So we're going to run EDB2 once again. So we're going to be in a loop. One thing to note, it says if B is set to 0 prior to instruction execution, then it's going to do 256 bytes of data. It's going to drag 256 bytes of data in. And we've also got some timing here to look at. Okay, so let's implement this. And the start of the implementation is going to be very simple, because what we're going to do, we're going to just grab this code. And I love it when we get to do this. And this is where, as I say, there's optimizations to be done, because all I'm doing is repeating code, and we shouldn't be doing that. We should be extracting common code, and we'll do that. So it's going to be INIR. So we're going to read a value from the port. We're going to write the value. We're going to increment register pair HL. We're going to decrement B. And then we're going to say, well, we're going to set the flags. And then we're going to say, well, is the value in B now 0? In fact, what we'll do is say not 0. So if it's not 0, what do we want to do? Well, what we want to do there is to decrement the program counter by 2. Rambling Geek, welcome to the stream. See you. Thank you for joining us. Not sure how long we're going to be going today. I've got a bit of a throat actually. But we started a bit earlier because I'm really pretty tired. So let's see if we can get some decent code written today and not fall into the trap we did last time of making silly mistakes. So if it's not 0, then we want to set the program counter. I'm going to decrement it. So that means we're now in a loop. We're going to go through INI as many times as it takes to decrement the B register and to 0. So that's kind of that. However, we go back to the documentation, it says that if B isn't 0, then we're gonna use an extra 5 TStates. You can see here, if B is 0, then we got 4, 5, 3, 4 TStates for a total of 16 TStates. That's 16 clock cycles will be used up by running this command. I've got a bit of a sore throat, yeah. Well, it's coming on through talking. I don't feel unwell, but I just feel a bit kind of dry. Yeah, so 16 TStates if B did reach 0, but if it's not 0, it's actually going to take an extra 5 TStates. So we need to account for that. So this is kind of the ideal, that it's 0 first time through, but we need to have the extra 5. Now luckily we can return here, returning 0. This is the number of additional TStates which our command takes. More wine required. I wish I had some wine today. I'm on orange squash in this Warwickshire Cricket Club plastic tumbler. Well, I don't feel well. I just seem to have a dry throat. So that's not the reason why I probably shan't go as late as I normally do. Just I'm quite tired. Okay, so what we need to do here, we need a var additional TStates. That's going to be 0. We're going to return additional TStates. He wants it as a byte, okay. And here, if B is not 0, additional TStates is going to be 5. So that kind of incorporates everything we need to do. We're going to whiz around this. We're going to whiz around this until we get to 0, and then once it is 0, then we pop out. Okay, so that should work. Now, what we could set, all this lot here is basically that command there, isn't it? So what we should be able to do is run ini pass opcode into it. So all the logic we built there now is being repeated, and all that happen is we should be able to run this through our tests now and see if we've actually got this working. First thing we need to do though is actually implement it. We've got the code, but we need to let our emulation know that it's there. So this is where for Dock in a Frock we can see how all this works. So there's these huge kind of instruction tables, and this is an ed command, I believe, so we need to find the ed instruction table. So unlike a simpler processor like the 6502, which had single byte instructions and therefore a maximum of 256 instructions, the Z80 had a lot more because it had multi-byte instructions, and it's reasonably complex the way it works. If we look over here at the operation list, you can see that you have opcodes prefixed by DD, by CB, by ED, or by FD, CB, or FD, DD in fact. And so you have an awful lot more, a couple of thousand opcodes. And we've coded all of these, and we're now on the very last part of this. So this was an ED. Let's have a look at what the actual operation code was. EDB2. That's here. So EDB2, we go over here. ED table, we want to find B2 in this table. So if we grab this, copy it down, B2. So this is INIR. That's the mnemonic value for our disassembler. We have implied addressing modes. Two possible addressing modes, all implied. And now we just want to call the function INIR. And now we need to set the TStates correctly. And here it was, and we used the minimum version. So without the additional TStates, the additional 5 TStates, that if it's not 0, 4534. 4534. Okay. So when we run our test now, we'll see what happens. We will be testing all of the register values, any final values, and we'll be testing how many TStates it uses up. So Rambling Geek, is it correct to say this is a CPU in software? It's exactly what it is. It's emulating all of the functions that a real piece of hardware would do, or most of them. Doesn't do exactly everything, I guess, because we obviously a real CPU, hardware CPUs, it's about voltage, high or low voltage lines, and we're kind of short circuiting some things like that. We're writing it in code, so we don't have to worry about a lot of the stuff that really happens on the processor. But we're trying to get as accurate as possible. So these timings, I've got it set so we're running at 4 megahertz. It's going to take slightly longer in reality on the emulation, but what I'm hoping is to be able to kind of adjust the values so that we can get running at approximately the right speed. It's not too bad at the moment, as far as I can tell. I don't know if you were here when I'll show you the Spectrum 48 screen in a second, Rambling Geek, but it does come up in about 4 seconds, and my understanding is the real Spectrum 48 would boot in 2 seconds, but that was all in hardware. Obviously, it was a hardware ROM. It was the memory was hardware, so it wasn't trying to emulate memory by having a 64K byte array. So I can't expect it. Probably takes a little while to initialize all that. I think we're in the right ballpark. Okay, so we've got that command now in there, INIR. Let's run our test and see what happens. So, in theory it should work, but I've learnt that you've got to really take it with it. Oh, it has worked. So now we're down to 119 not implemented tests, and we have 0 failing tests. So that worked straight off. It was pretty likely it would have worked, because we haven't implemented any new logic. All we've done, as I say, is simply add this thing with the additional TStates and to loop back if we haven't reached 0. So I don't know if you saw the Spectrum 48 thing I did, Rambling. I'll show you again. I'm sure you'd be interested. So if I start the default project here, you can see we do a bit of memory checks, and after about 4 seconds then we get the screen. Now with the original kind of borders, and something it approximates the right colour. It's not quite right. You had one, Rambling Geek. So can you kind of comment on, is this the kind of colour it was? Was it a greyish colour? Was the border white and the middle greyish, or was it all the same colour? And was it kind of grey background with black writing when it booted? I've seen some videos of it booting, and it kind of looks. I think the grey is not quite right, but it kind of looks like this. Yeah, it's obviously it doesn't do anything now. It's actually sitting there waiting for me to put input in, so to write a basic program. But we haven't got to that bit yet. but we're getting about up here. You can see the. I don't know if you can see. It's down here. This is the frames per second up here, and it's about kind of 50-ish. It was from memory. It was approximately these colours. I mean, they're not exactly the right colours because the Pixel game engine that we're using is using a slightly different RGB values, but I will adjust them and create a spectrum enum for the correct colours. Yeah, that's it. Okay, so we've got an INI command written, so that's another command off our list to write, and only 119 tests remaining. So what's next? Let's go and have a look. IND. So this is basically very similar to INI, except instead of incrementing HL, we're decrementing HL. It's got the same kind of weird stuff. It's saying it doesn't know what happens to some of the flags, but what we're gonna assume it's going to be the same as INI. So let's quickly write IND, sorry. Let's copy that down. It'll be IND. And this is kind of, once you've worked out how one opcode works, you can often kind of write quite a few just by cut and pasting, which is fine for me, you know, I don't mind doing that. So in this case, rather than incrementing register pair shell, we're going to, that's a -1, decrement it. Other than that, I think that should be it. So let's try it. So this is EDAA. We'll add this to our list. So it's going to be the same. Correct that error. AA. So let's grab this. The opcode is EDAA. It's IND. It's still got the same addressing modes. Implied. IND is the function we want to call, and this is 54534 TState. Let's see what this is. 4534 is exactly the same. Oh, we should be ready now to run our tests. Let's run that again. Fingers crossed. In fact, sometimes it seems to hang on doing this evaluation. There we are. We ignore that. So it's got 4 failing tests. So let's go and have a look at our failing test and see what it's failing. So looking here, mem pointer is pointing the wrong way. So basically what it's saying is mem pointer expected to get 55184, but it got 55186. So that's because we need to decrement mem pointer rather than increment it. So let's just stop that and go and have a look at the documentation for mem pointer. So it says for IND, it's the value before decrementing -1. Interesting. BC before decrementing -1. So over here, here's mem pointer. So mem pointer should be that -1 according to this. And mem pointer is, in case you're wondering what it is, it's a postulated undocumented register within the Z80. It gets someone has spent a lot of time working out under various circumstances using indirect, you can't go and look at the value of mempointer on the CPU. There's no way of getting at it. But from side effects, people have spent an awful lot of time involving theories about how it's set, what it must be on a byte by byte basis, and then using that to kind of build up some rules. Some of them more complicated than others. And the reason why we worry about mempointer is that A, we're trying to get the most accurate emulation we can, so it's got to pass all these external tests, but also some applications, mainly games, exploit the kind of idiosyncrasies of CPUs to get kind of special effects or better performance or whatever. So we do want to make it as accurate as possible, so we are trying to get this mempointer value correct. Right, okay, so let's now run our tests again and see what happens. So guys, if there's anyone out there who hasn't followed the channel, if you can see up in the top corner here, we're actually 3 off our target of 350 followers. So if you're feeling kind-hearted, I'd be really grateful for that follow. So let's just shoot Larry. Oh, it's interesting Pure Snowball. So that was quite a dodgy game back in the day, wasn't it? I never had that game, but yeah, interesting. Okay, so we're down from 4 fails to 2 fails. Let's see what's happening now. So so mempointers now, that error seems to have gone away. Mempointer's correct. It's saying that the value in AF expected as 0 got 17, and here expected 64 got 8. Interesting. So got 60, expected 64 got 68. So let's have a look what that actually means. Let's go into our programmer's calculator. So expected 64, so expected to have the flag here, this bit 6 set, but it got 68. So the 2 was also set in our case. So that's interesting. So let's have a look at what each of those flags mean. So if we go to our main Z80 class, so the 0 flag should be set, and it was set, but we also managed to get the parity flag set, and the test didn't expect that to be set. So let's go and have a look at our code and see if we can figure out why. So we're setting the parity flag that way. Okay, so let's go and look at the undocumented features. Let's see what it says. Okay, so it's got different calculations, look. It says which one was it? INDI used these calculations. So instead of C+1, it's C-1. Okay, so that should be fairly simple to fix. We go back to our code. Here we got a +1. That needs to be C-1. So let's run our test again. And now we've got no failing tests. And we're down to 115 unimplemented tests. That's good news. We're making headway. So, the next one is going to be INDR, I guess. INDR. So basically this is going to be exactly the same thing, except we're going to be doing a block. Actually, it looks slightly different according to that. That looks a bit weird. That's got to be a typo, hasn't it? Why would we put 131 into anything? I think that is some kind of typo. Let's have a read. So it says, yeah. So we load up the port into B and C. And 1 byte is from the selected port is placed on data bus written to CPU. Contents of the HL register pair are placed in the address bus, and the input byte is written to the corresponding memory location. HL and the byte counter are decremented. So yeah, so 131 doesn't come into it. So that must be some kind of typo, and it's not the first time I've come across typos and weird stuff in this document. Copy Verde, one of the first text games you played was Lords of Midnight. So you came into it late, obviously. Oh, I played Adventure or Colossal Cave on the university mainframe, which is why I've in our bot that's running there is a version of that text adventure that is running. So and it's work in progress. There's quite a lot of it there. There's some bits that aren't there, but it's a working adventure, text adventure, which you can play on through the bot, and you can play that on Slack or on Discord. It's not really. It works in Twitch chat through whispers. I'm not saying it's ideal. It's better in Discord or in Slack, but it does work, and you can get quite far. It's got kind of wandering monsters, wandering dwarfs in there, which can kill you, and lots of treasures and puzzles and secret locations to explore. All wonderful text adventure. Fun stuff. I like text adventures. The only problem with them is that the puzzles become so obtuse that I get frustrated. Okay, let's have a look. Let's copy this code. That's this INDR now. And then what we can do is, in fact, what we can do is just here. Oops, wrong one. The one we want. And this will be IND, and we'll pass in the opcode. We don't use the opcode that we pass in, but pass it in anyway. So there we go. That's that block instruction. So this is the way that the CPU can, through a single opcode, it can read in up to 256 bytes of data from a peripheral. Yeah, Lords of Midnight. I don't think I've ever played that. What was it about? What was the premise? Copy. Was it a fantasy, medieval fantasy type game, or was it science fiction? Okay, so we need to add this to our instruction table now. If we can find it, it was ED. Yeah, I think it would be here somewhere. So let's go and get what the. It's EDBA. So BA INDR. Oops. INDR, and the number of TStates 4, 5, 3 and 4. 4, 5, 3 and 4 with an extra 5 if it had to branch either as a non-zero value of B. Fuel Snowball, you worked on a text game called Trinity for 10 years. You finally solved it. Oh, you worked on it in that you actually were playing it. It took you 10 years to solve it. Yeah, and you managed to learn English from it. It's fantastic. Actually, I really love that that dungeon AI Dungeon, was it .io that you shared a couple of streams ago? I think it was on DevChatter's stream, and that was really good, and I enjoyed the adventures that you published about that. That was pretty funny. Okay, so let's we've got that. Let's run our emulator again. So we should get a passing emulation. AI Dungeon is brilliant. Yeah, I'm gonna have a play with that at some point when I've got some free time. So that's passed now, and we're down to 113 unimplemented commands or tests that I haven't got any code implemented to exercise them. Okay, so we're doing well. What's the next? So we've already done that, I think. We've done that one. So out I. This is out and increment. So it's very similar. Instead of pulling the value from the peripheral and then sticking that value, that byte we get from the peripheral, into the memory location pointed to by HL, we're now going to get the port number. We're going to get the value that's pointed to by HL and output that to the port value, the port pointed to by register C. So once we got unknown things here. When they wrote the manual, they didn't bother working out what it said, or they didn't care. As a programmer, you probably don't care what these values are. It's only as an emulation writer that we actually care, which is quite intriguing, really. That, we can happily write assembly language programs using this emulation, and it will work great, except where the program uses kind of bugs or tricks or undocumented features, and then we'll fall over because the relative flags won't be set. And that's the reason we want to get it as accurate as we can. So this is an output. So what I'm going to do, this is out an increment, wasn't it? Out I. Out I. Yeah. So what I'm going to do is simply grab the code for in I, and we're going to work with that. So we'll change this to out I. It'll be exactly the same, except we go in the opposite direction. This will be out I. So let's have a look. So what we need to do is to read from the bus. Read our value from the bus. So we're going to move this up here. We're going to say var n is going to equal read from bus we're going to read whatever is that memory location HL, and then we're going to write to peripheral. So here this is going to be write to peripheral, and it's going to be whatever's pointed to by BC, and it's going to be the value n is going to be written. What do I call it? Right peripheral. This is me forgetting. Let's have a look at what it's called. We go to our definition of IBIS. It's right peripheral. What's it mean? It's not. I'll reiterate, it's write to bus port. That's what I've called it. Okay, so basically this is an alias for that same write peripheral. Okay, so then we're going to increment HL, decrement B, and then there's all these flags here. So let's go and have a look at what those flags are supposed to be. Let's check mem pointer first. So for out I, so it's basically the same. BC after, it's after decrementing. BC after decrementing +1. Okay. So in this case, we need to set mem pointer after we've decremented B. So we've decremented B here, so we can set mem pointer there. So that's mem pointer. Now we need to look at the undocumented features of TState. And out. Take the state of L after the increment or decrement. Add the value written to the I port, call that K. If K is greater than 255, then CF and... Okay, so this is slightly different logic. Okay, so half carry and full carry flagged, so it's HL plus L greater than 255. Let's have a look at that. So that's N, whatever's pointed by HL. Plus L, wasn't it? So that seemed to be it. The value pointed to by HL, i.e. N, plus the value of L greater than 255. I think that's what we've got there. So the parity. So once again, we've got just plus L, very similar to the parity at the moment, except we're simply adding L in. X is going to be A and ANDed with 7, and then exclusive OR with a decremented value of B. That's the same as that. So hopefully that is correct. So the value of N then is still the copy of bit 7 of the value written or read from or written to the I/O port. Okay, so that should be sufficient. Let's code this up and see what we get in our tests. So over here, what was it again? It's going to be out I is EDA3. EDA3. So EDA3. So grab this. And here's the A3. And the out I is our mnemonic for the disassembler. Out I, and then function called is out I, and the TStates are the same 4, 5, 3, and 4. 4, 5, 3, and 4, yeah. So let's see how we do with that. Explorer, run the battery of tests. Okay, so that worked. So we're now down to 101 unimplemented TState unimplemented tests. That's not correct. Tests for which no code has yet been implemented. Okay, so that's looking pretty good. So it's better than last stream where these flags kind of causes a few more headaches. So what's next? It's going to be a block version of OutI, I reckon. OTIR, which is exactly what it is. So this is exactly the same, except we're going to loop. So we're going to decrement the program counter. So let's just copy this. Now we need to actually have this. OTIR. OTIR. And this is going to be OutI. Got the code in. And then if we haven't reached 0, we're going to decrement program counter twice and add in an additional 5 TStates. Is that correct? Yes, an additional 5 TStates get added if we haven't decremented B to 0 yet. Once again, weird stuff going on there. We're going to assume that all our flags are the same every time we run OutI. Okay, let's debug that. Once again, no planning tests, and we're down. Oh, that's interesting. 101 was the same number as before. Stop, make sure we've made no mistakes. B3. This, I've not referenced the correct thing. I think that's the problem. So let's go back there. It's not OutI, it is A3 should be TIR. Ah, no, wrong about. We haven't added it yet, that's why. So this is going to be B3, ED B3. I haven't added it yet. Okay. B3, this is OTIR. Once again, simple implied addressing, which is nice. We haven't got to figure out what the addressing mode is. Okay, so B3. Now we can run this again. We should either pass. I think we should pass, and we should have less than. Yes, we have passed. Now we've gone to 99, so it's an extra 2 tests run by that. Okay, making progress. OTIR, so let's have a look what the next one is. OutD, so this is the decrement version. Grab a piece of code. OutD. Here we're going to be decremented HL. D. Going to be -1, I suspect. Everything else, register per HL. Everything else should be the same. So if we're kind of really motoring now. This is AB, EDAB. So let's code that in and give it a try. EDAB. B there. C. apply register, pressing D. Okay, try again. When we're less than 100 tests not implemented, so we're really making good progress. So that's passed. Now down to 96. That's another 3 tests that were consumed. Right. The next one's going to be the block version of OnUpdate, isn't it? OnUpdate, OTDR. Okay, so we know how this works now. So we can quickly get that one in. That changes to a D there. There. D. And that's it. That's a -1 there. Okay. And that's OTDR. OTDR. So EDBB is our command. OTDR. OTDR. Okay, and the tests. So that's passed, and we're down now to 94. That's another couple of tests. 94 tests yet to go. Okay. Oh, we're really motoring. This is how I hoped to go last week, but it didn't work out. So, according to that, not yet. That is all of those input output commands done. So let's go a quick look at the operation list. Okay, so let's switch through. So we got as far as DDBB. And that was, so we've done those blocks there. We've done those. We've done those. We've done those. That's 1. Right, okay, 1, 2, 3, 4, 5, 6, 7, 8. So that's 8. What have we got here? Two, 3. That was ini. 1, 2, 3, 4, 5, 7, 8. So those are those set. And of course, the in A and out A, and in R and out R, they're not multi-byte commands. They're not multi-byte ones. So those live elsewhere. I don't remember where they are. Here they are. So they're just single byte commands. So we've, in theory, we've actually got to the end of what we need to code, but we've still got 94 unaccounted for tests. So let's go and see what they're actually running. Maybe I've missed some stuff. Let's run it up again and have a look at the non-implemented tests. And we've got DD00, DD00, and DD24, So let's have a look at DDZ00 and DD24. Give me a clue about what we haven't done. So here's DD00 isn't actually on my list. How interesting. Let's go and look at the undocumented Z80. So that's undocumented effect. The next bit is undocumented operations, DD prefix. In general, instruction following a DD prefix is executed as is, but if the HL register is supposed to be used, we use the IX, the index X register instead. Here are the rules. Okay. So I wonder what DD00 is then, because in that case 00 is a non-operation. 24 was the other one. Ah, look, there are some commands in there. I certainly haven't done increment the high byte of the index register and decrement the high byte of the index register. So there's a whole bunch of stuff here, and here's the low byte versions, look, which I haven't done. So let's take a look at 2.4. So 2.3 was increment, so it's DD23, increment the index register. In this case, what we're saying is just increment the high byte of the index register X, and there'll be a Y version as well. So FD24 will be increment the high byte of the IY register. So that's probably going to account for a fair number of missing instructions. Okay. So let's have a look at that. So we can close that down now. What we want is arithmetic. I believe we've got the increment and decrement in here. Let's have a look. Inc IX, there we go. So that's very simple. It doesn't affect any flags. So let's quickly see if we can write Inc IX H. We'll notate it like that. And we'll call it Inc H like that. So we need to find the high byte of the IX register. High byte equals IX, and we're going to bit shift that to the right by 8 bits, and then we're going to take the low byte, that's going to be IX, and we're going to AND that with 00FF, get the low byte, and then we're going to increment high byte, and then we're going to say IX is equal to high byte. Shifted state that way. That's the low byte. And that's all got to be cast as U short. And we'll have to take their word for it that it's not going to affect the flags. While we're at it, we'll do the Y version of it as well. It should be this. And it's going to be simply change these to Y's. Okay, so that was DD24 for that one. This will be FD24. So let's see if we have got anywhere near the truth with that. So we want DD instruction block. It's here, DD24. The 24's already there. DD24's already there. Oh, DDCB, DD2, just want DD. That's a triple byte instruction. DD, FD, DD, DD24, which is indeed missing. So we'll just pop in a new row here. So it's going to be 24. I want a new instruction. New list. Okay, so the instruction is going to be so the mnemonic is going to be inc IXH. It's going to be immediate X and the X. So we're just copying from the above. Sorry, it's implied, which is useful. And then it's going to be inc IXH, I believe I called it. And then what's the well, we're going to assume it's the same, aren't we, for the timing, because the undocumented commands don't really tell us what the timing is. There we go, those are the ones that we're looking for. So we have to assume the timing is the same, as the timing will be the same as this here. 4,6 the TStates. Okay, so that's that one. So let's do the Y version, because it's all mirrored. Where there's a DD, there's the same. There's an FD version of, except that's looking at the Y index register. We change the mnemonic to Y and function we're going to call to Y, and we'll see what happens. Okay, let's go and just quickly check the code again. Logic. Okay, so let's cross our fingers and run this. So this will run our test. Remember, we had 94 tests remaining, and we got 2 failures. We got 92. So let's have a look at what went wrong. So there's a couple of problems with each. So the timing was wrong. It says it took an extra 2 TStates, and the flags are different. Okay, so let's look at the TStates. Is it saying it took longer? So the timing, expected 8 got 10, so actually it took less time. It took 2 TStates less. So let's sort that problem out first. Now I'm going to assume that it's actually going to be 4 and 4. 2 lots of 4 TStates. We'll do that. We haven't got any hard information on this, so we are not exactly guessing, but we're deducting that it's going to be that. Okay, so now we've only got 1. So this it says our status register expected 1672. I'll just make a note of this. Expected 1672, but got 1688. So let's have a look at what 1672 and 1688 actually represent. So go on to our programmer's calculator again. So we'll put in a decimal value of 1672. And what we're interested in is these last 2 nibbles here. We're not worried about the top nibble. So this is the status register. So it's saying the sign, it's saying it's expecting 1000 1000. That's the sign bit has been set. And it looks like one of the undocumented has been set. I think that's undocumented flag U. So it looks like the undocumented flags are being set. So we can soon sort that out. Okay, let's try something with that. So I'm wondering if the increment flags, same flags as a set when you increment something, should be set. So let's go and have a look at the helper for increment. So we've got a helper file tucked away somewhere. Helpers, and in here there's some flags that get set when we increment something. I'll find it. Set inc flags. So what we could do is try running that and see what happens. Set inc flags. Not saying this is correct, but we're going to try it. So for here we're going to say set inc flags, and what it wants is the original value and the incremented value. Change this slightly. Let's say var val equals pi byte plus 1. That into there, and then we'll pass IBIS and incval into there and just run that one. The byte. Casting is always a problem here, so let's cast this byte. There we go. The same here. Okay, so we'll leave the IY version of that alone. DMJ, welcome. Yes, I haven't seen you for a long time, so welcome. Good to see you. We're deep into undocumented features of the Z80 process at the moment. So I can't find any written down about how the status flags get set when you do these undocumented operations. So we're going to have a play and see what happens. So let's debug our tests. So we've only got one failing test now. So if we look at our failing test, this should be on the FD version, FD24, yeah. So my guess was accurate, I believe. So all we need to do to get the other test passing is to go over here and simply grab this code, drop it down into here, and then change the X's to Y's. Like that. And then run again, see what happens. Yep, so we're now passing all our tests, and we're down to 92 tests, still not passing because the code hasn't been implemented. That's the way to say it, isn't it? Okay, so over to our opcodes again. So we've done inc. There's obviously a decrement version of this, which is 25, but also there's increment versions for the low byte of the index register. So there's some really strange commands here. Look at these ones here. So obviously we're not going to do a lot of these this evening. Let's do the decrement versions, the increment versions, sorry, of the low byte of index register X, because that seems like a logical thing to do. So let's grab this code. We'll say this is going to be low. Increment the low byte. In this case, we don't care about the high byte. Okay, so we do kind of care about the high byte, so let's bring that back. So we've got the high bytes and we've got the low bytes. Now we're going to say we're going to increment the low byte. And then we're going to say, and we'll find better ways of coding this, but we're going to do the minimum. If think val is now 0 because we've incremented it, and it's got obviously if it's a single byte, if it's FF, we increment it, it's going to go to 0. Then we also want to increment the high byte. High byte is going to be Incval. This is going to be high byte. Going to be low byte. And we need to class that as a byte. Like that. Okay, so that's once again pretty speculative. What command is that? That is 2C. Let's just do that one for DD2C. See where we get. The DD2C, the gap in there. So let's just grab that bit of code there. 2C. Pop it in there. So this is increment the low byte. And this is simply an L there. We're going to guess it's going to take 4 and 4 TStates, so 8 total TStates. So that's what's that? On a 4 megahertz machine, that's going to be like 2 microseconds. Let's see what happens when we run our test on that one. So that actually passed by the look of it, and we're down to 91. That has decremented, doesn't it? It was 92 before. So let's have a look at our passing test. DD2C, wasn't it? Quite a few of them now, as you can see. DD2C, passing test. Okay, I believe it was DD2C. So we're passing there. So now we can write the code for the Y version and the Y variant of that. Put Y's into here. And that'll be FD2C. Copy that entry and then move down to the FD instruction table. FD2C. We can run our tests again. And we got one failing test. What's it saying? Interesting. FD2C. Okay, I must have got something wrong. Stop. And that's over here. IY. So that's just when we thought we were understanding what was going on. It's why is it testing IX at all? IX. At the high byte of that, at the low bytes, increment the low bytes, 0, then increment the high byte. Is that the wrinkle? The incrementing value is 0, then we have just incremented beyond the value. It must go to 0, and we must carry a 1 into the high bytes. I'm a bit baffled by that one. Try it again, just see if we can get any pattern. So it's failing. It's definitely FD2C, saying that the first failure, it looks like we didn't decrement IX, and we did decrement IY, but that's what it's asked to do. So let's have a look at the tests. So it was FD2C. These are the tests as the kind of created in Fuse, and we have a program which reads these tests and interprets what has to happen. We've got FD2C. FD2C is coming up. Here it is. So here's the IX and IY register values. So the expected D2C. We also have a reader which interprets the results, and that's what gives us our nice output, tells us what's wrong. So it's saying the results should have been B9. B9 8, so it should have incremented that one, but it seems we've affected the wrong way. Let's go and have another look. I can see what the problem is. This has got 0 references. So all that's happened is that I've not updated this line to be IX. It should be IY. Okay, so that explains it. Okay, so let's now try again. Debug that. And we're now passing. And we've got 90 unimplemented. Okay. So I think that's probably a good time to start to think about ending. What I will do just before we finish, I'll just recap on some of the things that we did earlier. So people have been dropping in and out. I know that. So we got Chris in now. So we're very close now to having our Z80 implementation, Z80 emulation complete. There's a few little things we still need to do, specifically around very specialized types of interrupts that you can call. But by and large, we're nearly there. We've got a handful of these undocumented instructions to do. So another 90 tests that need to pass. We've already kind of got about 35 tests that have now passed during the stream. One thing we've done with the emulated Z80 is created a little test suite here, and also a little example suite, which is running the Spectrum 48K ROM. And if I run this up, we're using Javid X9's Pixel game engine to display the screen of the boot screen of the Sinclair ZX Spectrum 48K. So this is the ROM running. You can see it's running about 50 frames per second. Nothing happening at the moment because we've got no interactivity. But this is the boot screen. These colours aren't quite right, but I will fix the colours. But that I think Rambling Geek says he remembers that that's what the boot screen looks like. So we're pretty good there. We've also got a debugger. So if I run the debugger, let's set that as being the startup project, and run the debugger. We've got a nice Windows Presentation Foundation application here, which is our visual debugger. What I can do is I can load programs, or I can load ROMs in here. So let's load the ROM, 48K ROM. It's now going to disassemble that. Here is all the code that's been disassembled from the ROM. There's 16 kilobytes of program code and data. Yeah, you've got some data here. You see, it hasn't disassembled the data. We have a file which tells the disassembler where the boundaries are, where we have data. And this is the ASCII character equivalent, just in case it's of any use to us. We can single step through this program. Now it's pretty pointless to do so, but we can do it. We're going to start at our program counter at 0, and we can step in, and you can see the various flags are being set. Plenty of mem pointer and queue, and all these the status registers here are all being set as we single step through the code. We're now in the memory check section, so we're testing memory at the moment. The other thing we've got here is something that FeelStable has contributed. It's a writable bitmap. It's a screen. It's a bit like it's meant to work a bit like the Pixel game engine screen works. It's not actually wired in at the moment. It is refreshing itself every 20 milliseconds. Nothing being written to the screen at the moment. There's a few kind of wrinkles about how I implement this so that we get some kind of visual representation of what's going on. It'd be really nice to have something displayed here as it puts values into video RAM. We get some kind of value. So, but that's a work in progress. I've got some thoughts about how we're going to do that. Just have to think about it, and also work perhaps with FeelStable on getting that working. So with our emulation now, we have a reasonable suite of tools. We've got a I'll just set this as a start project. We've got an emulated CPU, which is very close now to being complete. It's taken a long time to do. We've got a nice visual debugger. There's some things we need to do into that. We need to complete the display of the stack. Yes, we need to run in a separate thread. So we're going to build a run button and try and run the CPU in the background. CMJ. So that's how we're going to get that working. But at the moment, it's FeelStable. I haven't even worked on that bit yet. I did a few things on, I think, last Thursday, just to establish that when we run the CPU, it blocks the UI thread. So I'll kind of set that aside. That's all on GitHub. If you want to do some work yourself on that FeelStable, if you feel so inclined, please feel free, because it's not something I'm going to be concentrated on just yet. I want to get the CPU implementation completed, and also I want to start looking at getting some input into the Pixel game engine. So I've got to work out exactly how that works. I think it works through interrupts. So I've got to kind of figure out how the Spectrum 48K interrupts work. We can call an interrupt easy enough. I don't know which ones to call. Luckily, we've got this wonderful resource, which is the Spectrum ROM map. And from here, if I look in here, routines, you can see 0 101820. These are the interrupts. These first 1, 2, 3, 4, 5, 6, 7. These first 8 little blocks of code are the interrupts. So there's a mask interrupt routine. There's a calculator restart. There's a collect next character, which is interesting. Select character, print a character. So there's lots of kind of clues into this, but I need to kind of work on figuring out how it's actually going to operate. But really, kind of my objective for the kind of medium term is to get that Spectrum 48K kind of model. We won't call it an emulation. We call it a model, so that I can program in BASIC in it. Then maybe we'll do a stream where we learn some BASIC. I don't know. That'd be quite interesting to do. And that'll be working on my emulation. That's kind of the idea, is to have some way of demonstrating that the emulation works and does something useful. Then we'll package up the Z80 code into a NuGet package and stick it up on NuGet so anyone can download it and use it. The other things we've got a nice comprehensive test suite. This sample project is dead now. I shall probably be removing that from the code base, because the Spectrum 48 is the sample code I'd like to ship with the repo. So as I said before, if you haven't followed the stream, I'm only three followers away from reaching my 350 target, so I'll be very grateful for a follow. If you haven't watched all of my streams in the past, all of them are archived on YouTube. All but one, in fact. There was a stream using a plastic building block, which I removed because of the copper legislation. It might be interpreted as being for children. I didn't want to do that. So that's my YouTube channel. We have a Discord. If you'd like to join in any kind of post-stream discussions, there's my Discord. I've got a Twitter account. You can follow me on Twitter for the latest news. I don't post that often, but sometimes I will. It's actually, that command hasn't worked, has it? Anyway, my Twitter handle is up on the screen anyway. But yeah, if you'd like to subscribe to my YouTube channel, that really helps me out. It's completely free to do so. And this video will be up on YouTube this time tomorrow. I tend to post them straight away. I don't edit them or anything like that. They're just exactly as they kind of were streamed. And there's loads of interesting projects on there. At least I think they're interesting. There's a synthesizer written in WPF. There's an Alexa skill written from scratch. There's Microsoft Bot Framework. There's secure REST API. There's plenty of things to keep you interested. There's even some C++ and some F# stuff that do with FuelSnable, and there's a whole sequence on doing shaders, 2D and 3D shaders. So this kind of effect that we use on the stream, this is a shader. This is one that FuelSnable created very kindly for the stream. It's called this hyperspatial hype. I really do. And then there's this one, which is Electric Alpha, another FuelSnable special. I really love that one. That's what we use when we get a follow. And for raids, there's this one which we built on the stream. This is Alf launching into space, and that rocket plume is a shader, so that's being created in real time. You have some new ideas for 2D shaders? Well, we must get together, FuelSnable, because we're well overdue for another shader stream. We were working on text shaders, and we need to kind of link up now and get that back in gear. Indeed, this is a shader as well in the background. You can't see my hand, can you? There we are. All these stars going by. This is a shader as well. All being generated in real time. It's not a video. It's actual pixels being painted on the screen in real time. They're all hosted upon static website. I think it's fantastic what you can do. There's a whole bunch of those, especially some really interesting ones on generating terrain. So that's mountains and lakes and clouds and water and all kind and trees in the landscape. Check that out. So I'm glad you have got some ideas, just now. I think 2D shaders are pretty interesting in their own right. The 3D ones and ray tracing is good, but the 2D shaders have some merit themselves. So I'm glad that. Yeah, I do like this. Starfield. When you have a few teraflops, yeah, it's easy to do, isn't it? Okay, so thank you very much for dropping by on the stream today. I may or may not stream on Wednesday. It's a bit difficult at the moment because there's real life issues going on. We're going to be busy organising a funeral, basically, over the next couple of weeks. But once that's all out of the way, we should get back to normal routine. So thank you, Copperbeardy. Good to see you, and hope to catch your stream fairly soon. It won't be this week. I shan't be around this week to catch your stream, but do enjoy your stream as well. So thank you. Okay, so let's find someone to raid, shall we? Who can we raid? Let's have a look. So who's live? So we got Saw Scoot, we've got Jitter Ted, Lana Lux. So Lana's got a lot of viewers. So let's raid Saw Scoot, shall we? So if you'd like to stay on the channel, and we'll go over to Saw Scoot's channel. He's another one of the live coders, and I will see you either on Wednesday, unlikely, but certainly next week, same time, around about 7:30 to 8 o'clock, something like that. So take care, everyone, and I'll see you again soon.